Welcome to another course of continuing education for professional engineers. This course will focus on the impacts of nitrogen and hydrogen on LNG. Now, typically we think of LNG as being only hydrocarbons, methane, ethane, propane, etc. But we don't think of having nitrogen in LNG. But if your feed gas has nitrogen, freshly made LNG will also contain nitrogen. As far as hydrogen is concerned, historically and presently, it's not a concern of having hydrogen in the LNG because it's not in the feed gas. However, for environmental reasons, there's been a lot of initiatives that have been underway that are projecting injecting hydrogen into the pipeline system across the United States. If that does occur, it will end up being part of the feed gas going to LNG facilities, and through the production facilities, small amounts of hydrogen may end up in the LNG. If it does, it has problems associated with it, and we will discuss some of those.
A little bit of information about myself. I'm a PhD in mechanical engineering. I have a master's degree in both mechanical engineering and civil engineering. I've taught undergraduate and graduate level engineering courses at a university level. I have 52 years of gas industry experience. I retired from Keyspan Energy in 2004 as Vice President and Chief Engineer. Today they are known as National Grid. I have 20 years of international and domestic experience in teaching and consulting on LNG projects across the country and around the world. I have a passion for LNG safety, for developing human resources, and for ensuring that our gas industry is reliable.
The learning objectives are as shown here. We're going to examine the zeotropic fluid volatility behavior, speak about interchangeability, talk about segregating inventories if you have multiple tanks, the properties of nitrogen, the properties of hydrogen, the effects of nitrogen in feed gas of liquefaction systems, the effect of hydrogen in feed gas on liquefaction systems, the effects of nitrogen on LNG storage, the effects of hydrogen on LNG storage, the effects of nitrogen in bog, that's boil-off gas, the effects of hydrogen in bog boil-off gas, and how to remove nitrogen and hydrogen from the feed gas or from the LNG before it goes into the tank storage. And we're also going to talk about hydrogen stress corrosion cracking, which is a concern when you're dealing with hydrogen and certain materials under stress conditions. Unfortunately, hydrogen and nitrogen sound so similar that I may have to designate it as nitrogen with an N or hydrogen with an H during this presentation. Small quantities of nitrogen are usually found in natural gas, and they are undesirable when they go into a liquefier because they decrease the efficiency of the liquefier and they end up increasing the nitrogen content significantly in the bog, that is the boil-off gas. Nitrogen can also be detrimental to fuel cells. So if you make LNG and the LNG has a small amount of nitrogen in it, that LNG gets vaporized, sent out to fuel cell customers, it can have a negative impact on the fuel cells. Depending upon the concentration of the nitrogen in feed gas, it can also reduce the temperature of your LNG that's stored. And what we have to be careful is our tanks are, for the most part, and I'm talking about large atmospheric tanks, are rated at minus 260 degrees Fahrenheit. If you get colder than minus 260 degrees Fahrenheit, we'd be operating outside of the design range of those tanks. Hydrogen with an H is not normally found in feed gas, so it's not been a concern in the past. However, for environmental reasons, there's a lot of pressure being put on the industry to consider injecting hydrogen with an H, into the transmission system, and that would become feed gas for LNG liquefiers. there's still a lot of research that needs to be done before that can be done safely and reliably. Hydrogen, if introduced into feed gas systems, can render a LNG facility dysfunctional, and there may need to be hydrogen removal systems installed, and we will talk about that. Both hydrogen and nitrogen will have a significant impact on the bog production of a liquefaction facility because both of them are very volatile gases and they outgas very rapidly. So if you have nitrogen, let's say, is at 1% in your feed gas, you may have 20% in your boil off gas, which is quite significant. Before we get into the meat of this course, let's talk about some fundamental definitions. What is a pure substance? A pure substance is a homogeneous substance that's the same everywhere. So if I looked at a cube and pointed at any point within that cube, I'd point to one particular component, and it would always be the same component. That's what we're going to define as a pure substance. So if I had a cube that was filled with pure carbon, everywhere I pointed within that cube, I'd find a carbon atom. If I had a cube that was filled with pure methane, everywhere in that cube, I'd be pointing at, instead of saying a carbon atom, I'm saying a methane molecule. And it does not have to be an atom that I'm pointing at. It could be a molecule. If it's the same everywhere, that's a pure substance. What is an element? Well, an element is the simplest form of a pure substance that cannot be made any simpler by chemical reaction. For instance, methane, CH4, that's carbon atom connected to 4 hydrogen atoms. Well, that is not an element because it can be separated into the pure substance carbon and into the pure substance hydrogen. So it is a pure substance, but it's not an element. Volatility is the propensity of a fluid to change from a liquid to a gas. So gasoline is very volatile. The fumes of gasoline come off of the gasoline and can be ignited. But methane is much more volatile because it's, as a liquid, it will evaporate very rapidly as it were to be warmed up. What is the critical pressure? Critical pressure is a point, a pressure level below which you can have liquid, solid, and vapor. But above the critical pressure, you can only have a fluid or a solid. There's no such thing as liquid or vapor above the critical pressure. It's strictly a fluid. And what makes the difference between a liquid and a vapor? Density. So as you increase pressure, the density of vapor becomes very close to that of the density of liquid, and eventually the two become the same. So the density of liquid becomes the density of the vapor at the critical point. And above that critical pressure, you only have a fluid. No liquid, no vapor. Next, we will talk about zeotropic fluids and the volatility of zeotropic fluids. Zeotropic fluids are fluids that, when mixed together, have different boiling points. Now, they do not boil off sequentially, but they boil off preferentially, which means that, let's say I had 1/3 methane, a mixture of 1/3 methane, 1/3 ethane, 1/3 propane. Well, these three components have three different partial pressures. So what I would see is, in the liquid, I'd have 1/3, 1/3, and 1/3. But in the vapor, I'd have almost 99% methane, some ethane, and just small, very trace amounts of propane. That's how a zeotropic fluid will off gas, and it's dependent upon the partial pressure within the liquid and the partial pressure within the vapor. Each component has its own propensity to change from a liquid to a vapor. The volatility of a zeotropic mixtures refers to how readily the mixture components evaporate or outgas. As I said, with methane, ethane, propane, the methane has the highest volatility. If I put nitrogen in there, then the nitrogen is even more volatile than the methane, and the nitrogen would preferentially boil off. Now, when I say preferentially, it means that yes, some propane will boil off, but very small amount. A lot of hydrogen would boil off if hydrogen were in there. A lot of nitrogen would boil off. Some methane would boil off, some ethane would boil off, and trace amounts of propane. And I've listed those in stating them just now in sequence of volatility. Hydrogen being the most volatile, nitrogen next, methane next, ethane next, propane last in that listing. Because of the above, the bog that's coming off an LNG storage tank will always be much different than the composition of the LNG itself. This is the periodic table. It's a table of all the elements. Keep in mind, elements are pure substances that cannot be made any simpler by chemical reaction. And they are organized in periods, shown here, periods being 1, 2, 3, 4, 5, 6, 7. And these are periods, and these columns here are also known as groups. So you have groups 1 through 18 as shown here. And looking at the far left, we see the alkaline metals. The far right, we see the noble gases. Next to the noble gases, we see the very reactive halogens. Then we see the nonmetals shown here. And we have all this large grouping in here of metals. And we also have transition metals. They're not quite metals in properties, and they're not quite nonmetals, so they're called transition elements, sometimes called transition metals, sometimes called transition nonmetals, because they're not metal and they're not nonmetal, somewhere in between. And that's where our transistors that use these materials for switching from a nonmetal property to a metal property. Then we have this guy, hydrogen, over here. And hydrogen really didn't have a home, so it was decided to put it here. However, it's not one of the alkaline metals in the way it reacts. So hydrogen really doesn't belong here, but it needed a home, so this is where it was placed. If we look at hydrogen, it has one proton, atomic number 1. So it's only a single proton with a electron spinning around it. Now, in a very rare case, you'll find a hydrogen that has a proton and a neutron. That's deuterium. That's going to be an isotope of hydrogen. And you'll also have tritium, which is another isotope. So because of that, the molecular weight of, or the molecular mass of hydrogen is not 1, but it's 1.008. And what happens is there's a very small amount of deuterium and tritium found in nature. So we are going to consider hydrogen only as a single proton with one electron on its outermost part. And we're going to talk about hydrogen and how it reacts. And because it's only a single proton, it's a very, very small element, or very small atom, I should say. Now, hydrogen is found only as a diatomic molecule in nature, meaning it's going to be H2, two hydrogen atoms bound together. And of the diatomic molecules, there are only 7 of them: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromide, and iodine. Those are all found in nature as having it as a molecule, meaning they're 2 atoms bound together. We're going to talk specifically about hydrogen and about carbon and about nitrogen. And if we looked at hydrogen, it's got a molecular weight, we'll say, of 1. Really, it's 1.008, but for simplicity, we'll say it's 1. But it's found in nature as H2, so it's going to have a molecular weight of 2. Nitrogen, again, found in nature, it's shown on the periodic table as having a molecular mass of 14. We've rounded it off to 14. It's really 14.007. But it's found in nature as a diatomic molecule, so it really has a molecular weight of 28. Now, carbon is just carbon, not diatomic, and that has a molecular weight of 12. Now, if we combine some of these elements together, let's combine one carbon atom with 4 hydrogen atoms. We get CH4, which is methane. And what's the molecular weight of methane? It's 12 plus 4 hydrogens. That gives me 16. Now, in reality, it's 16.004, but we've rounded it off to 16. Let's say ethane. Well, ethane would be C2, which is 2 carbons at 12 molecular weight of 12 each. So that's going to be 24 plus 6 hydrogens. So it's 24 plus 6 gives me molecular weight of 30. Let's say we took propane. That's C3H8. Well, 3 C's gives me 36, that's 3 times 12, and 8 hydrogens would give me another 8 onto 36 would be 44, molecular weight of 44. That's for propane. I didn't show propane here just for space reasons, but you get an idea of the difference between molecular weights of different chemicals found in nature, or different molecules found in nature. Now, you're not going to find nitrogen by itself. It'll always be N2. You can find carbon by itself, and you can find a molecule of CH4, that's methane. You can find a molecule of ethane, molecules of propane, molecules of hydrogen, and that's some of what we're going to be discussing as we move forward in this course. On this slide, we show the components of LNG and their volatility. Now, I'm showing hydrogen, even though hydrogen is not in the past or is not presently within LNG, and that's why I show it as typically as 0, but it may be a component of LNG in the future. That has a boiling point of minus 422 degrees Fahrenheit. That's 16.5 psi A, absolute. And I've selected that pressure because that's a typical pressure of an LNG storage tank, large size LNG storage tank. Nitrogen concentrations, that's nitrogen with an N, are typically between 0 and 1% when the LNG is freshly made. So it's freshly made, it might have 1%, and it'll, over a relatively short period of time, I'm talking like order of magnitude of a month, it will drop down significantly from 1%, and that's because it has a very high volatility, as shown here, of minus 319 degrees Fahrenheit. Again, we're talking at this tank pressure. Methane, which is the major component of LNG, typically between 87 and 97%, that has a boiling point of minus 256 degrees Fahrenheit. Ethane, minus 124 degrees Fahrenheit. Propane, you typically think of propane at minus 44 degrees Fahrenheit, but that's at atmospheric pressure. At this slightly elevated pressure, the boiling point is minus 39. And here's the molecular weights, which we've already spoken about on the earlier slide. Typically, LNG does not have very much C4 plus hydrocarbons. Typically, you'll find trace amounts of butane, pentane, hexane, and hexane would be very, very little, and anything higher hydrocarbons would be. You'll never remove every molecule, but there'll be only trace amounts. Boil-off occurs preferentially and not sequentially, which means in the boil-off, if there's hydrogen in your LNG, you're going to have a lot of hydrogen outgassing very rapidly. You'll have your nitrogen outgassing very rapidly, and your next gas that would preferentially be boiling off would be the methane shown here. Composition of the LNG and boil off is always different. So if you, whatever your LNG composition is, the boil off will be different because of the different preferential boiling points, or different volatilities, I should call them. Weathering changes the higher heating value and the density of the LNG over time. And what weathering means is that over a period of time, the LNG weathers, meaning gets rid of or outgasses its highest volatility components more rapidly than a low volatility components. Doesn't mean the low volatility components will not outgas, but they'll outgas at a slower rate proportional to their percent composition in the LNG and proportional to their volatility temperature. Composition of the LNG drives the LNG temperature, and it also drives the bog composition. Here we're taking a look at a mixture of 96 molar percent of methane and 4 molar percent of ethane LNG. So only two components in this LNG, 96% methane, 4% ethane. When we look at that, and here's our liquid phase, we have 96% methane, 4% ethane. Let's take a look what happens in our vapor phase, the boil off. The boil off is 99.99% methane, and yes, there's a trace or a small amount of ethane, and that's because preferentially the methane boils off. What would happen over a long period of time? Well, this concentration of methane in the liquid form would decrease, and the composition of ethane would increase. So at some point, this may end up being, let's say, 80% methane and 20% ethane over a long period of time. What about the temperature? Well, the temperature is driven by its composition. Here we're looking at minus 255.6 degrees Fahrenheit. And that would be true for both a saturated liquid and a saturated vapor. Let's take a look at a different composition. Now we're looking at 95% methane, 4% ethane, 1% nitrogen, nitrogen with an N. And if we look at it here, it shows here's our 95% methane, 4% ethane, 1% nitrogen. What do we have in the boil off? Well, earlier we had a 99% methane, but now we only have 77 or 78% methane. Why is this so much lower? Because the nitrogen is showing 22% concentration. And of course, yes, there is some ethane, but it's only a trace amount. So now what dominated is the nitrogen, certainly preferentially boiled off, but because there's only 1% nitrogen in liquid state, we're getting 22% nitrogen in the vapor state. Methane, we have 95% methane in the liquid state and 77, almost 78% in the vapor state. What happened to the temperature? Well, remember this nitrogen is only 1% in the liquid state, shown here, and 22% in the vapor state, but it's highly volatile and it's much colder than methane. And notice what it's done to the temperature. Now the temperature is minus 260.8 degrees Fahrenheit. If it did not have the nitrogen in it, it would have been minus 255, as shown here. Take note that just 1% nitrogen resulted in more than 22% nitrogen in the bog, and that 1% nitrogen also lowered the temperature by 5 degrees Fahrenheit. Hydrogen with an H has not in the past been a component of LNG, nor is it presently a component of LNG. However, there's been a lot of discussion about injecting hydrogen into the national gas pipelines, and if that happens, it will become part of the feed gas to LNG liquefaction systems. When hydrogen in the LNG feed gas, most of the hydrogen passes right through the liquefier and ends up in the flash gas. That makes bog management difficult. If you get, let's say, 5% hydrogen in the feed gas and you condense out all of the methane, ethane, propane, etc., what are you left with but almost pure hydrogen going out in flash? And that really won't be the case because you'll get something. You'll get hydrogen plus methane, ethane, but it'll be in much smaller concentrations of the methane, ethane, and your boil off gas will be significantly high in hydrogen content. That becomes problematic because what do you do with a stream that's, let's say, 50, 60% hydrogen if your gas system uh, is not designed to handle that level of hydrogen concentration? The higher the temperature, the more concern there is of hydrogen stress corrosion cracking. That's where hydrogen reaches a stress point in the metal, in the whatever the material is. Typically, it's metal, but it reaches a stress point in the metal, becomes monatomic hydrogen, migrates actually between the grain boundaries and into the metal, meets up with another hydrogen monatomic hydrogen atom, and becomes diatomic hydrogen, which now produces a bubble or a gap within that metal, which becomes a stress concentrator. So it concentrates more and more. And the hydrogen tends to go where the molecules are the furthest apart. Where are the medical molecules furthest apart? During the highest stress points of the metal, or the highest tensile stress points in the metal. Hydrogen is listed as not being compatible with 9% nickel steel. That again is problematic because 9% nickel steel is what most of the tanks, LNG tanks, are made of. Several papers have been published that state hydrogen in feed gas will reduce liquefaction efficiency and make liquefiers, maybe even make them dysfunctional. So there may need to be hydrogen removal systems upstream and within the liquefaction plants of today. Hydrogen is such a new topic with relation to LNG that the scientific evidence is just not available to predict how it will impact liquefaction systems, storage systems, and send out safety and reliability issues. R&D is in progress on hydrogen and LNG. Thermodynamic softwares do predict how hydrogen will react or will behave, I should say, not react, but will behave when making LNG. However, the thermodynamic softwares are at their limit because if you use two different thermodynamic software programs, they may not match the same data output. So there's question about which information is correct. You'll see some data that has been extrapolated from thermodynamic software. You'll see that in further slides. Here we see the thermodynamic display of projected values that would come out of an analysis for an LNG concentration that has some hydrogen in it. And you'll see that to overlay the data, what I've done is basically overlaid one set of data on top of another set of data. And I crossed out, in this case, in this particular program, I was showing 0.05%, 0.05% hydrogen in the LNG liquid, and the other program showed 0.15% hydrogen in the liquid. So that 3 times the amount, but there's still very small amounts of hydrogen in the liquid. And this is where the contradiction comes up. In both of these cases, we're showing 52% hydrogen in the boil-off gas, or 0.05 to 0.15% hydrogen in the liquid, talking 52% hydrogen in the boil-off gas. We're talking about a liquid density that has increased significantly, not because the hydrogen is heavier, but because the liquid has gotten so much colder that it contracts. So here we're looking at a liquid temperature and a vapor temperature of minus 270.86. That is problematic because our tanks are designed, or most tanks are designed for minus 260 degrees Fahrenheit. So how do you handle LNG that's at minus 270 degrees Fahrenheit? It becomes a real problem. Will the tanks self-stratify, auto-stratify? We don't know at this particular point. At least the literature does not dictate it or does not show enough information. And R&D analysis is just not available to show whether the stratification will be an issue. R&D is still in progress. Presently, LNG does not contain hydrogen, but if hydrogen does get mixed into the feed gas, these questions will need to be answered. Let's move away from hydrogen for the moment and talk about interchangeability of natural gas send out. Remember, natural gas, which comes from vaporizing LNG, needs to be interchangeable with pipeline natural gas. Now, there are no hard and fast rules for that because the natural gas composition is different all around the country. But FERC, the Federal Energy Regulatory Commission, did put out a white paper that most people use as their guidelines. And their FERC guidelines are that your send out needs to be 1,110 BTU standard cubic foot maximum. Your Wabi number, which is a unitless number, needs to be less than 1,400. The total amount of inerts, that's non-hydrocarbon gases, needs to be less than 4%, 4 molar percent. Your CH4 components need to be less than 1.5 molar percent. And the Wabi number needs to be within 4% of the historic Wabi number for those customers. And this is all based on a standard cubic foot with an STP, standard temperature and pressure, of 14.73 psi absolute and 60 degrees Fahrenheit. And we need to be careful with this standard cubic foot or standard temperature and pressure because different industries use different values for STP. The Wabi number is a unitless number that is the higher heating value divided by the square root of the specific gravity, and it's shown here mathematically, HHV divided by the specific gravity to the 0.5 power.
I mentioned weathering on the slide earlier, and I didn't explain it. So let me go over what weathering is. As your tank sits there idle, no pumps are running, and your tank is just gaining heat from the environment, boil off is occurring, meaning that some of your LNG is converting from liquid to vapor. What boils off? Essentially a most volatile component. So that would normally be, if you had nitrogen in your gas, would be nitrogen. But let's take a tank that has no nitrogen content. So methane would be a most volatile component within the tank. Methane would boil off, leaving behind the ethane, propane, and any other heavier hydrocarbons. So in this case, we're going to start off with a concentration of 93% methane, that's C1, 5% ethane, remember that's a bit high, that's C2, 1.84% C3, which is propane, and a small amount of the heavier hydrocarbons, C4 plus. I said there's no nitrogen in this LNG, so that gives us a total molar content of 100%. So now what happens as weeks go on, days go on, some of this methane boils off, and you see the methane concentration getting less and less and less. But the molar concentration of ethane remains the same, and the propane remains the same, as does the heavier hydrocarbons. Well, what does that do to the higher heating value? Take a look here. Higher heating value starts off at almost 1080 and ends off here at 1085, and that's in week 23. And the Wabi number, as shown here, goes from 1393 up to 1397. We're bumping right up against that 1400 limit that FERC requires. So this is what weathering is. And on the next slide, we'll look at it, taking it to from week 23, we'll take it to week 52. Let's continue with this spreadsheet, looking at how weathering affects BTU value and Wabi number. Week 24, we're at 0.85 moles of C1. If you remember, we started off with 0.93 moles of C1. We're looking at 0.05 moles of ethane and 0.0184 moles of propane. Wabi index is 1397 and higher heating value is 1086. Over time, let's look at week 52. And in week 52, the higher heating value has raised up to 1095, quite high, and the Wabi number is now 1402, which is in excess of what's allowable by the FERC guidelines. Let's take a look at what has happened to the mole percentages of the different components. Here we have 91.4% methane, 6.1% ethane, and 2.2% propane. What has happened is preferentially the methane has boiled off, the ethane has remained the same, and the propane has remained the same. Thus, if you look at the total mixture, you see that it is now a lesser percentage of methane and a higher percentage of the higher heating value components of ethane and propane. And that's why when you're selecting a site, you have to make sure that your feed gas is appropriate for the LNG that you want to make. And if it's not appropriate, you're going to have to do some more pretreatment. The more pretreatment you do, the more costly the plant will be.
Let's take a look at the properties of some potential components of LNG. And I say potential components because one of them, hydrogen, is not presently a component, but it may well be a component in the future. So let's take a look at methane. Methane is typically 85 to 95% of your LNG, and methane has a molecular weight of 16. Where do we get that 16 from? If you recall, when we looked at the periodic table, carbon had a molecular weight of 12 and hydrogen had a molecular weight of 1. So this is one carbon atom and 4 hydrogen atoms, adding up to a molecular weight of 16. The higher heating value is 1013 or 1013 BTUs per standard cubic foot. And the effect you have on LNG is the more methane you add, it lowers the BTU content of that LNG because it's the component with the lowest higher heating value, assuming you're not adding in nitrogen and hydrogen. But of the hydrocarbons, it's the lowest. This is methane, ethane, propane. There be some higher hydrocarbons, there be pentane, although those will not really be any significant amount of that in LNG. And what effect does it have on Wabi number? Well, the more methane you have, the lower the Wabi number. What effect does it have on the temperature of the LNG? It makes it colder. The more methane you have, the colder the LNG gets, and that's because it has the highest volatility, which we already discussed. Ethane, C2H6, that's 2 carbons, so that would be 24 plus 6 hydrogens, which is 6 times 1, is a total of 6 hydrogen on the hydrogen. We end up with a molecular weight of 30. And we have a higher heating value of 1,775 BTU per standard cubic foot. Increasing the ethane content increases the higher heating value, and it increases the Wabi index. A Wabi index and Wabi number are the same thing. Sometimes you use the word index, and sometimes you use the word number. If you add ethane to an LNG mixture, it makes it warmer. And if you recall, the ethane has a much warmer boiling point, somewhere around minus 122, in that order of magnitude degrees Fahrenheit. Propane C3H8 has a molecular weight of 44, a higher heating value of 25, 24, so it significantly increases the BTU content of your LNG, which would be a higher heating value, significantly increases the Wabi index, or the Wabi number. And it makes the LNG warmer. That's because you recall propane has a boiling temperature of somewhere around 40 degrees at atmospheric atmospheric pressure, and I say somewhere around 40 degrees, depending upon what atmospheric pressure is. At 14.73, it might be minus 44 degrees Fahrenheit, but we measured it at 16.5 psi absolute, and that came out to 39 degrees Fahrenheit, minus 39 degrees Fahrenheit. Nitrogen is an interesting one. Nitrogen has a molecular weight of 28. And why? Because in nature, nitrogen is not found as a monatomic atom. It's found as a diatomic molecule, which is N2. And if you remember, the molecular weight of nitrogen was 14. 2 times 14 gives you 28. Interesting, the heating value of nitrogen is 0. So as you add nitrogen, it lowers your higher heating value of your LNG mix, and it lowers the Wabi number. And it makes the LNG colder, significantly colder. And the reason it makes it colder is because, if you recall, the boiling point for nitrogen was somewhere close to minus 320 degrees Fahrenheit. At 16.5 psi absolute, I believe the number that we had calculated earlier was minus 319 degrees Fahrenheit. Hydrogen, which boils off at minus 422 degrees Fahrenheit at 16.5 psi absolute, has a molecular weight of 2. Even though hydrogen has a molecular weight of 1, it is always found as a diatomic molecule, which makes it H2. And it has a much lower heating value than any of the other components other than nitrogen. It has 325 BTU per standard cubic foot, which gives us a little bit of a dilemma if it is injected into the pipeline, transmission pipeline, because the total transmission pipeline higher heating value would be reduced. And how do you deliver the same amount of energy to customers? The only way to do that would be to deliver more standard cubic feet. So to deliver more standard cubic feet, you're talking about higher velocities in your pipelines, and it's going to be a challenge that yet has to be evaluated. What is the effect on higher heating value? I just mentioned it lowers the higher heating value. It also lowers the Wabi index, and it makes the LNG much, much colder. And as you remember before, we looked at like 0.05, really small amounts, 0.05 to 0.15% hydrogen in LNG. And we were talking about temperatures in the order of magnitude of minus 270, really cold LNG. And the reason why I highlight that minus 270 is because of two things. One, it degrades the efficiency of your liquefier. Two, it may be colder than the design of your equipment. And there's another effect that I didn't mention, and that's that it may even make your liquefier dysfunctional. You may not be able to use the liquefier at all without removing the hydrogen first. In the past, hydrogen has not been a component of LNG. It's only lately been discussed as a future component. Now, the problem is when you try to model it with present thermodynamic models, we get different answers using different models. So physical experimentation needs to be done to validate the modeling, and there's very little of that information available, and experiments are being done as we speak. looking at the effects of hydrogen on LNG.
If you have the luxury of having multiple tanks, you can segregate inventories between tanks where you have high BTU LNG separate from low BTU LNG. And then when you're called upon to make send out, you can mix the two and thereby meet the FERC requirements of the FERC guidelines. This is called blending.
Well, so far I've mentioned nitrogen as being a negative when it came to LNG, but sometimes we actually intentionally inject nitrogen into our send out. Let's say we have a tank that has a high BTU content and a high Wabi index content in the LNG storage, and we want to decrease the higher heating value, and we want to decrease that Wabi number to make the gas interchangeable. Well, remember from the FERC guidelines, we're allowed to have up to 4% inerts in our send out. Well, inerts are anything that will essentially not burn, not have a heating value. Carbon dioxide would be an inert, nitrogen would be an inert, and there are a number of others, but the one that's used in the industry is nitrogen, and it's used to lower the higher heating value to lower the Wabi index. So you have to have an air separation plant on site or a large storage of nitrogen so that you can inject that nitrogen into your send out to lower the BTU content and to lower the Wabi number in the event you have a storage of high BTU LNG that needs to be made into send out. So an LNG facility that does stabilization typically has air separation plant on site or nitrogen storage. Now this is called stabilization. This is called stabilizing the send out. Here I give you an example of nitrogen stabilization. I'm starting off with a mixture of LNG that is 89% methane, 9% ethane, and 2% propane. It has a heating value, a higher heating value, which is computed as shown here. 0.89 times its heating value, that's methane, 0.09 times ethane's heating value, 0.02 times propane's heating value, for a total heating value of 1,111.8 BTU per standard cubic foot. That is higher than what's allowable by the FERC guidelines, and a Wabi number of 1,417, and that's also higher than the allowable Wabi number based on the FERC guidelines. And I'll point out here that the Wabi number is a unitless number. So don't look for units after the Wabi number. Sometimes it's called a Wabi index. So let's take this potential send out and let's add 1% nitrogen to it. Now what'll happen, all of these other percentages will decrease slightly. These will be 0.99 times 89. This will be 0.99 times 9%. This would be 0.99 times 2%. Going through this, and here you see the new mixture: 88.11% methane, 8.91% ethane, 1.98% propane, and of course we have 1% nitrogen. What is the new heating value? It is 1,100.7 BTU, which is well underneath the 1,110 BTU, so that satisfies the FERC guideline. The new Wabi number is 1,398.95, which satisfies the guidelines. This must also satisfy the Weaver index, which we've not covered and we will not cover it in this course. But there's another interchangeability index called the Weaver index, and that is also applied to the send out in order to make sure it's interchangeable. If you have a high nitrogen content in your feed gas to a LNG liquefier, it is likely that you will have a high nitrogen content in your LNG. Perhaps your feed gas has 3% nitrogen in it. your LNG might have 1% nitrogen in it. Having nitrogen in your LNG can cause a non-stratified tank to auto-stratify, and then you can get subsequent rollovers. And as we mentioned earlier in other lessons, rollover is a serious risk or a serious event that can be hazardous as well as can discharge significant amount of vapor bog to the atmosphere. To avoid having rollovers, some terminals, import terminals, will restrict the nitrogen content delivered to their facility. Now, typically, the literature shows that 1% nitrogen in LNG will cause autostratification. My own studies and analysis shows that as little as 0.26% nitrogen in LNG will cause a reversal of the density change that occurs as your LNG weathers. So I'll go as low as saying 0.26% is a concern, but in general, the literature says at 1%, you will get auto stratification. Now, the interesting thing about the 1% is it says that you'll get auto stratification, a rollover, then another auto stratification, and a rollover. So that clearly points to the fact that it's something less than 1%, because when you get that first rollover, you discharge a lot of nitrogen. And the fact that you get subsequent rollovers tell me that the real number is something less than 1%. And I came out to in my own analysis, to 0.26% as being the inflection point where the density changes from being, if it was no nitrogen, your density continuously gets more dense. But if you have nitrogen in your LNG, the density becomes less dense, and then eventually, as your nitrogen gets low enough, the density starts to increase. You'll see that graphically shortly. This brings us to the point where we can discuss weathering, which is a boil off over a period of time with and without nitrogen in the LNG. Let's take a look first as LNG without nitrogen weathers. What happens to its density? Its density becomes greater. And why? Because methane is also the most volatile component in LNG without nitrogen. So it boils off, and it is the lightest component with a molecular weight of 16. As you remove the molecular weight of 16 component, you're left with the ethane, which has a molecular weight of 30, and the propane, which has a molecular weight of 44, and the entire mixture becomes heavier with time. As LNG with nitrogen weathers, preferentially, instead of losing only methane to boil off, you also lose nitrogen. Keep in mind, nitrogen has a molecular weight of 28. So instead of losing methane completely with its molecular weight of 16, you now also lose nitrogen with a molecular weight of 28. If the concentration of nitrogen is high enough in the LNG, you'll lose enough 28 molecular weight component that you actually have the density become lighter rather than heavier over time. And why is that? And that's because the nitrogen will be the component with the highest volatility. The more nitrogen there is in the LNG, the more pronounced this effect will be on lowering the density as it boils off. This is demonstrated on some of the slides that I'm about to show, and we'll see how nitrogen can affect the potential for stratification and subsequent rollover. First, we'll talk about the stratification that occurs when you have a fill stratification. That means that you intentionally put a heavy LNG under a light LNG, or a light LNG on top of a heavy LNG. And you may intentionally have done that, but it's a mistake because that causes stratification. Over a period of time, that lower layer, let's say this was the original heavy LNG, well, this lower layer cannot cool down, but it's continuously gaining heat from its surroundings. So what happens when a liquid gets hotter? It's not boiling off. It doesn't have a surface it can boil off at and cool down. So it gets hotter and hotter. Well, as it gets hotter, it expands. So its density decreases and it becomes light heated LNG. This is over a period of time. Originally, it was heavy LNG, it was dense LNG, but now it's less dense, it's lighter. Also, what's happening to the top LNG layer? Well, the top LNG layer is weathering. So it's becoming more dense. So this top layer is becoming more dense as the bottom layer becomes less dense, and there's an instability here. Eventually, you end up with this bottom layer being lighter than the top layer, and the two flip. Now, no one really knows whether it flips or rapidly mixes, but many people depict it as a flipping, and many people also depict it as a rapid mixing. One thing is for sure that when a rollover does occur, whether it's a flipping or a rapid mixing, tremendous amount of boil off is produced, more than the tank can typically handle. Relief valves open, and it's an uncontrollable event which you have to avoid. To avoid such an event, typically you have a densometer that goes up and down, traverses the tank, and it also a temperature reading that traverses the tank. Now that's true in newer installations, but some of the vintage tanks do not have that capacity. So you avoid rollovers by very careful operation of the plant. Once a rollover begins, it is self-perpetuating. It actually accelerates itself. And that is because as the liquid rises, this warm liquid rises to the surface, it sees less and less pressure. As it sees less and less pressure, bubbles start to form within the LNG, and the bulk density drops significantly, causing it to rise even quicker to the surface. And that's where you get this high boil off taking place. Let's take a look at the mathematics of weathering without nitrogen in the LNG. This is a composition of 96% methane, 4% ethane. And over a period of time, it loses some of its methane concentration in the liquid form, and the percentage of ethane actually increases over time. Looking at that, what happens to the density of the liquid that's in the LNG tank? It increases over time. So this, as time continues along, the density keeps getting more and more increased until eventually you have a very dense LNG, and it can be an interchangeability problem because with that increased density, you get a higher heating value. Why? You're losing the methane and you're keeping the ethane. Let's take a look at what happens when we do this now. The same mathematics, but instead of doing it without nitrogen, we're going to do it with nitrogen in the LNG. Here we're looking at the mathematics of weathering with nitrogen. So this is with nitrogen in the LNG, and we started off with a composition of 95% methane, 4% ethane, 1% nitrogen. And that 1% nitrogen starts right here where it says 0.0099975, essentially 1% nitrogen. And as you weather, this nitrogen content goes down and down and down and down and down because that nitrogen is boiling off rapidly. In fact, initially in your boil off, you have 22, almost 23% nitrogen in your boil off. Let's take a look at what happens to the density. The density here is getting, instead of getting more dense, it's getting less dense, less dense, less dense, less dense. And then at some point, it turns around and starts becoming more dense. Why did it turn around and start becoming more dense? Because you've reached the inflection point where the nitrogen content is so low that its boil off is much less nitrogen in it and more methane in it. So it starts now to increase the density. So you get an increase in density from that point on. So from initially, it's making the LNG less dense, and then eventually it stops and turns around the other way, and the LNG becomes more dense. And by these calculations, it shows this happens for this particular mixture at about 0.26% nitrogen in the LNG. Take a look notice of one other thing that's I find extremely interesting, and that is that the temperature, the saturated temperature of the mixture initially is minus 262.3 degrees Fahrenheit. Very cold. Probably colder than what the tank is designed to withstand. The tank is designed for typically minus 260 degrees Fahrenheit. Now, it may just be a technicality, but it is a concern that has to be addressed. Your tank is designed for minus 260 and you're operating colder than minus 260. Well, that can be a concern. But look at what happens over time. The LNG mixture becomes warmer and warmer and warmer and warmer. What happens when a liquid gets warmer? It expands. What happens when it expands? Its density goes down. So that also adds to the density going down. Not only the loss of the higher molecular weight component being nitrogen versus methane, but also the fact that the liquid is warming up and it is expanding as it's warming up. Here we're looking at some modeling output of weathering without nitrogen in the LNG. And I selected 95% methane, 5% ethane at a temperature of minus 256.36, which is the saturation temperature at the surface. And the assumption here is that this continuous mixing puts the temperature at the bottom of the tank at the same temperature as at the top of the tank. Now I add 1 degree Fahrenheit, make it warmer at the surface. Where does heat come from? Came from the bottom as well as from the sides. And this 1 degree temperature increase has lessened the density. How did it lessen the density? Well, the LNG liquid expanded. So the density becomes less and this becomes lighter than its surrounding LNG, and therefore it rises, causing a convection current. And it rises until the evaporation takes place at the top. When evaporation takes place at the top, we have less methane, more ethane, and this becomes more dense. 0.178 being more dense than 0.161. So this now drops to the bottom of the tank and the circuit starts all over again. And this is a normally circulating tank that does not have nitrogen in it. And you can see how this will continue to occur as this gets warmer on the sides, evaporates on the top, drops to the bottom, and continuously has convection current taking place within the tank. This is important when you think about pumping LNG because it's important that this LNG here be at the same temperature as this LNG so that it becomes subcooled LNG because of its pressure head. So for this temperature, and this pressure, this is subcooled LNG, and this on the surface is saturated LNG. Remember, to operate a pump, you need subcooled LNG, and that's why if you have a submerged pump, you have subcooled LNG in the pump tube, or if you're taking a bottom withdrawal, you're taking subcooled LNG from that bottom and feeding it to your LNG pumps. Let's do this same numerical analysis, but this time let's start off with a concentration of 94% methane, 5% ethane, and 1% nitrogen. We heat that nitrogen, methane, ethane mixture up by 1 degree and it becomes less dense. Why did it become less dense? Because it expanded. And as it expands, it becomes lighter and causes these convection currents to occur. But as it evaporates, what happens is it becomes slightly heavier, but not heavier than the bulk LNG that's in the tank. So instead of it dropping to the bottom, Look at this density here. It's 27.581, and what's in the tank is 27.626. It does not want to drop to the bottom, and it starts recirculating within itself. As it recirculates within itself, it again evaporates more nitrogen off and becomes even less dense than the bulk density. And then you'll see over a period of time, what happens is you get a separation of two layers of LNG. This slide shows a tank without nitrogen content and one with nitrogen content. And you can see how the difference in circulation pattern occurs once you have nitrogen in that LNG. You start to form this top layer. Let's take it a step further. Once this top layer forms, the bottom layer actually starts to circulate within itself. And you end up eventually having two separate layers as shown here, an upper layer and a bottom layer. Now this bottom layer has no way to cool off, so it keeps getting warmer and warmer and warmer. And as it gets warmer, what happens? It expands. And then eventually the density of this bottom layer becomes lighter than the density of the top layer, and you have a rollover occur. Look here at the density here. This is 27.35. This is 27.397. So this is heavier, this is lighter, and you get this flipping that occurs. Either it's a flipping or it's a rapid mixing, but either way, you have a nitrogen-induced stratification with subsequent rollover. Here we are graphically showing the two compositions of LNG, one that has no nitrogen in it. As you can see, the density continues with time, continues to get more and more dense. And here you see a LNG mixture that has nitrogen in it. And as you can see over time, it gets less dense, but it starts to level out. This graph to the right takes a different mixture, but it takes it over a longer time period. And as you can see, the density with the nitrogen in it comes down, reaches some flat or level point, and then starts becoming more and more dense. So it actually has a reduction in density before it has an increase in density, whereas the LNG that started off without nitrogen in it just continuously gets denser over time. Well, thus far, we've concluded that nitrogen in your feed gas is not a good thing, and too much of it will cause high nitrogen content in your LNG. So if we have too much nitrogen in the feed gas, how do we remove it? The easiest way to remove it is to go through your liquefaction plant and then knock it out in a nitrogen removal column called an NRU. NRU is nitrogen removal unit. Now, some nitrogen removal units are nothing more than a knockout drum where the flash goes out the top and you can remove the high nitrogen content. But some of them have to actually be a distillation column because you need reflux and boil up to occur within the distillation column to better separate the nitrogen from the LNG. So let's look at this process as shown here. We have natural gas coming in. This is your feed gas with high nitrogen content. It goes through your pretreatment system, goes through your liquefaction plant. What do we have here upstream of your JT valve? You typically have 100% liquid. Flash across your JT valve, have liquid and vapor. The vapor is high nitrogen content. It rises out and is removed. Now, also in this vapor is also high methane content, so you can't just discharge this. This will typically be added to your bog and sent out to the pipeline, or maybe perhaps it's used as fuel for consumption needs within the plant. And then you can pump your LNG, this is low nitrogen content LNG, into your LNG tank. This is for removing nitrogen from the feed gas of the LNG facility. Now let's take a look at a unit that can remove both hydrogen and nitrogen from the feed gas. Now, hydrogen is desirable to remove most of it or as much as you can before it ever gets into your LNG facility. And the reason is you really don't want hydrogen in large quantities to come through your pretreatment system and go through your mole sieve, which is going to be heated up to 550 degrees Fahrenheit during regeneration because of the hydrogen stress corrosion cracking concern. So you typically would put in a hydrogen removal system up front. This could be a membrane system. There are other possible systems that could be used, but a membrane system would probably be the most cost effective, removing most of the hydrogen here. Nitrogen is slipping through, so you have small amounts of hydrogen and nitrogen slipping through, goes through your liquefaction facility. Now, the fact that you have both nitrogen and hydrogen in here means that this LNG that ends up here is going to be rather cold. So you can take the liquid from here and use it in a recondenser, because if it's colder than the liquid that's stored in your tank, you can take this bog, boil off gas, and recondense it into liquid using the cold LNG that came off your NRU to recondense it. Now, why did I use a recondenser here and not earlier? Because now this LNG has a small amount of hydrogen in it, and that hydrogen makes the LNG very cold. So you end up now with sending almost pure LNG to your tank. It's pretty much devoid of hydrogen and nitrogen, and you take your bog gas and you can send that out, and your off gas from your NRU gets sent out. Now, keep in mind the bog gas off your NRU is going to be high in nitrogen and hydrogen content, and this has hydrogen gas in it as well. These two streams can get mixed together and then managed however the plant chooses to manage that stream. Hydrogen is not something that we've had a concern about in the past in LNG facilities, but it might be in the future. So let's just touch upon some of the concerns. Hydrogen leaks require very little activation energy to ignite. In fact, if the hydrogen is concentrated enough, it can almost auto-ignite. The flame speed of hydrogen in a fire is so fast that it is prone to detonate instead of deflagrate. The explosive range for hydrogen is much broader than natural gas. Natural gas is roughly 5 to 15% gas and air, and hydrogen is between 4 and 74% hydrogen in air. Hydrogen flames burn hotter than methane flames. A hydrogen molecule is so small that it'll often leak through leaks that would not occur if it was methane in the gas stream instead of hydrogen. So let's say a threaded fitting might be acceptable with a with methane or some combination of methane and ethane, propane, etc. But if you have hydrogen in that same gas pipe, it would leak through. In fact, hydrogen molecules are so small that they weep through solid plastic piping. So that's a concern in the distribution system. Finally, let's talk about hydrogen stress corrosion cracking. In order for hydrogen stress corrosion cracking to occur, you need three components. You need hydrogen, you need a high stress point, and you need a susceptible material. Hydrogen obviously is needed. Hydrogen at the surface of the material goes from a molecule of hydrogen, H2, to monatomic hydrogen, becomes H right at the surface of the material, single hydrogen atoms. A single hydrogen atom is nothing more than a proton with an electron. It is extremely small. It slivers between the other molecules of the material and meets up with another hydrogen atom and becomes a hydrogen molecule again. And now that adds a gas pocket within the material. So this steel or whatever else it is that is now under stress has porosity in it. It has little gas pockets within that steel, and that becomes a weak point. As that steel stretches further, that hydrogen follows that stress point all the way until eventually you have a full crack that takes place. You need to have also susceptible material. That susceptible material depends on the structure of the material, whether it's austenitic or martensitic, and also the other parameters that are associated with the specific design, certainly stress levels, material, amount of hydrogen, etc. In fact, the amount of hydrogen will just accelerate the hydrogen stress corrosion cracking if it's higher, but it will not prevent it. There's no minimum amount of hydrogen that's necessary to create hydrogen stress corrosion cracking, and that's according to the Sandia National Labs. Hydrogen stress corrosion cracking is also much more susceptible at higher temperatures. So I think about the mole sieve regeneration vessel in the LNG facility. Well, the mole sieve, to regenerate it, you have to bring it up to 550 degrees Fahrenheit. High temperature, high propensity for hydrogen stress corrosion cracking. Most LNG tanks are made of 9% nickel steel. That is the inner container of the tank itself. 9% nickel steel has been identified as not being compatible with hydrogen because of stress corrosion cracking. However, what's unknown is how it behaves at very low temperatures, cryogenic temperatures. That's where more research is needed. In conclusion, a lot more research is going to be needed for hydrogen within LNG facilities. Well, our conclusions about nitrogen and hydrogen in LNG are as follows. High nitrogen concentration in an LNG liquefaction feed gas is not desirable, but with today's technology, it can be managed. Adding nitrogen to LNG send-out is acceptable practice to keep send-out interchangeable. Adding hydrogen to an LNG liquefaction feed gas is problematic, as many of the ramifications have not yet been concluded. More research is needed.